the first Thursday of most months, and the next one is going to be on Thursday, October the 2nd. Now, the next tour will also mark the first tour of the 2014-2015 season, and this being the last of 2013-2014. And the only reason why we make that distinction is because every September we elect a new executive to run the AstroTours. So before I continue, I'd like to just take a moment to mention all of the dedicated and hardworking people who've helped run the tour in the last year. Starting with the executive, there is Lisa Estevez, who helps us find and train our volunteers. Andre Vayner, who does all of our marketing and our graphic design. Elliot Meyer in the back over there, who is our webmaster, social media guru, and what's the other thing you do? Oh yeah, you record the tours and you put it on YouTube. What am I missing? Jai Li Zhang, who is responsible for tour logistics, which means all of our equipment, as well as the cookies that you guys love so much. And lastly, Michael Williams, who, among his many, many jobs in this department, also maintains our planetarium and our telescopes. Aside from our core executive, we had 3 special projects people this year. Sergei Osakan, who is responsible for rebuilding the website, so we now have a new website. Peggy Salby, who is responsible for our expanded feedback program, and Evgeny Kissin, who is responsible for bringing Rocky Pole here in June. Aside from our executives and our special projects, we have to thank all of our volunteers. These are the people, the undergrads, graduate students, and postdocs who every month dedicate a portion of their time to working on the tours, be it to run a talk, or to man a telescope, or to run a planetarium show. The AstroTours could not function without the dedicated work of both our executives, our special projects people, as well as our volunteers. So if you could give everybody who worked on the AstroTours. You are currently in the lecture portion of our event. Once this is over, there is going to be a Q&A period of a certain number of minutes with our speaker. And following that, we're going to have simultaneous planetarium shows and telescope observing. I'm going to be telling you about how to get to those after the question period is over, so please stay seated for post-hoc announcements. Tonight, we're going to be talking about telescopes, new telescopes. And ever since Galileo built his telescope up to the Hubble Deep Field, the creation of the new telescope has often come hand in hand with revolutions in astronomy. And now, astronomers are building the next generation of enormous telescopes high in the Chilean mountains and deep in the Australian outback. What will those telescopes tell us? What will they discover? Tonight, Dr. Laura Newburgh will give us an overview of the future of observational astronomy. Laura did her PhD in Princeton, and then, PhD in Columbia, and then did a postdoc in Princeton where she built microwave telescopes. She's currently a Dunlap Fellow who is working on the CHIME telescope to help uncover the secrets of dark energy. Take it away, Laura.
Oh, thanks. This is the moment where everything broke before, so let's just hope for the best. That looks promising. All right. Okay, so I'll be talking about dreaming big with big telescopes. So first of all, light is a wave. That is the assumption I'm making for the whole rest of the talk. So just to put it out there, light is a wave. So keep that in mind. We're pretty familiar with waves. We know about waves from basically every part of our existence. There are waves in the ocean and in water. There are waves in slinkies, and most of you probably are old enough to know what a slinky is, but for the rest of you, there's probably an app to figure that out. Sound waves are also waves. So when I talk, I make pressure waves that make their way over to your ears, and you detect those. And you can prove that in the way that all physicists love to with fire. I won't be doing that today, and you shouldn't do it at home, but it's possible, and there are some nice YouTube clips about it if you're interested. So light is a wave, and we know about waves. Waves have a lot of interesting properties. The one that I'm focusing on today is wavelength. So wavelength is the distance, so a wave, right, it's a thing that goes up and down. Wavelength is the distance between a peak to a peak, or equivalently, you know, a trough to a trough. But a wavelength is a peak to a peak, and long wavelength means that distance is large, and short wavelength means that distance is short. So short wavelength means short, long wavelength means long. Because light is a wave and waves have wavelengths, light has wavelengths too. So it turns out that our eyes are light detectors. They operate between 400 and 700 nanometers. Red light operates at 700 nanometers, and violet light is down at 400 nanometers. So wavelength has units of meters or nanometers, etc. So red light has a longer wavelength than violet light, which has a shorter wavelength. Energy is also sort of related to wavelength. So red light with its longer wavelength is kind of lazier, it's not as energetic, it takes a little longer to get there. Violet light, on the other hand, is much more energetic, it bounces up and down much faster. So more energy with shorter wavelengths and less energy at longer wavelengths. I don't happen to know usually how big a nanometer is, so I looked it up, and it turns out 400 to 700 nanometers is somewhere between the size of a virus and a bacterium. So just to give you an idea of how big a wavelength is for our eyes, what our eyes can see, it's a size somewhere between a virus and a bacteria. So if our eyes could see the entire night sky, they would see, and have great resolution like a telescope, they would see something like this. So we live right here in the Milky Way galaxy. This is our home. A galaxy is just a collection of stars that are bound together. So we live in one of those, and we call it the Milky Way galaxy. There are also other stars and stuff out in the night sky, and there are some other bright objects. For example, the Large Magellanic Cloud down here, and the Small Magellanic Cloud, which you can see basically with your naked eye in the southern hemisphere on a dark night where there's not a lot of light around you, for anyone who's traveling there in the near future. So our eyes see visible light, but it turns out there's a lot more wavelength where that came from. So we operate right here in the visible. It turns out that's about in the middle of most of the wavelengths of light that we can actually detect as people who build detectors. So we can detect light all the way from gamma rays. So this is tiny. These numbers are in centimeters. This is 10 to the minus 12 centimeters. That's tiny. That's about the size of an atomic nucleus. So atoms like hydrogen have nuclei inside of them. So this is an absolutely tiny little thing. Because energy is like wavelength, this means these are extremely high energy light. So this light has a lot of energy in it. We can detect all the way down to radio waves, which are the size of people and buildings even. And this is much lazier light. So this wavelength is huge. It's very low energy light. And we're just sitting right here in the middle, so we can see things that are about the size of bacteria. So there's a lot of light out there that we can see if we could only build detectors that could do it. So astronomers do this. We build detectors that go out and measure stuff in the sky. So we exploit the fact entirely that there's all this wavelength of light that we have access to. So if we look at the gamma ray sky, if we put on our gamma ray glasses like this Yama, we would see a sky that looks like this. So it doesn't seem particularly interesting. For the most part, it's just blue, so there's not much going on. Again, we can see here's our Milky Way galaxy, and there are a bunch of little point sources. So like I said, gamma ray light is extremely highly energetic. So there's just a lot of energy in this light. And there aren't a lot of things that can make a really energetic light, right? As far as astrophysics is concerned, it's collisions, it's explosions, it's stuff spinning around and spewing light out at extremely high energies. So there aren't a lot of things that do that, which is why most of the sky is blue. And then there are some little sources, and these happen to mostly be stars that exploded. If we reorient ourselves back to the visible sky, I had pointed out a couple of things, the Large Magellanic Cloud and the Small Magellanic Cloud. In gamma gamma rays, there's just nothing going on, right? So those two galaxies, they're not visible in gamma rays. There's just nothing energetic happening in them. So that's sad, but oh well. There are also two other things. The North Galactic Spur totally doesn't exist. This will show up at a few other wavelengths, so just keep your eyes on this and on Centaurus A. So in gamma rays, those are pretty dim or non-existent. Same with large and small Magellanic Clouds. So really, gamma rays are just the most energetic things that are going on in our universe. And so there aren't too many sources in the sky like that. But they're also fascinating, right? It's stuff that's super energetic and really interesting, and we can't access those energies on Earth. So this is really an interesting place for astrophysics, because it's the only place you can test extremely high energy stuff. So if we step down a little bit, down to X-rays, we put on our X-ray glasses like Superman, the universe looks a little different now. So still the Milky Way galaxy is pretty clear. We can see we're living somewhere in the middle. And X-rays are still pretty high energy, but not quite as high as gamma rays. So stuff that gave off gamma rays will probably give off X-rays too, but we're also seeing a few other things pop up now at these slightly lower energies. So the Large Magellanic Cloud, suddenly a little visible in X-rays. Centaurus A, nothing too much going on there. It still looks pretty dim. And there's this huge spur called the North Galactic Spur, and that's starting to show up in X-rays. So the X-ray sky looks pretty different from the gamma ray sky. If I just go back and forth, suddenly a lot more stuff is starting to appear. If I go back down to visible, so this is again our familiar night sky that we would see with our eyes. The large and small Magellanic Clouds start popping up. Again, here's our Milky Way galaxy, and Centaurus A and this North Galactic Spur have disappeared, so there's just nothing. If we step down yet again to a lower frequency, a longer wavelength, so we put on our microwave glasses instead. This is what we would see in the night sky. So again, here's our Milky Way galaxy, familiar as always. The large and small Magellanic Clouds now suddenly getting brighter. And Centaurus A, yep, there it is. Someone even put a nice circle around it for me. And the North Galactic Spur, there's still some kind of thing happening here. So it's pretty obvious, unlike in the visible. So as we step through these different wavelengths, a lot of different astrophysical phenomena start becoming more clear. So doing the sort of multi-wavelength astronomy is really useful for figuring out what's going on. And then finally, if we put on our radio astronomy glasses, we see an entirely different sky. So again, here's the Milky Way galaxy. It's basically bright at all wavelengths. The large and small Magellanic Clouds are these little dots. Centaurus A is super bright, and the North Galactic Spur is pretty bright as well. So astronomers use all these different wavelengths to understand what's going on in our universe and to figure things out about interesting astrophysical phenomena and things they see in the sky. So this is ultimately the tools we use to understand the universe around us. So I'm going to zoom in on this guy, on Centaurus A. And we're going to ask throughout the course of this lecture what exactly Centaurus A is. But I can tell you, this is what I got from Wikipedia. Centaurus A, it's a galaxy that's currently consuming a nearby galaxy, and it contains a supermassive black hole at its center. So a black hole is a star that exploded and then collapsed on itself and is so dense that not even light can escape. So that's a black hole. A supermassive black hole is just a really big version of that. So we know what Centaurus A is, but how do we know all of that? And that's what we're going to answer in this lecture. So hopefully you'll be able to answer that at the end. That's my goal. But first we're going to take a little meandering detour to tell you just how astronomers actually figure this stuff out. And it turns out mostly we just make bigger and bigger telescopes. So over time, telescopes, they really just keep getting bigger. So it started out with just our eyes. If you look at the moon, for example, with your eyes, you'll see something like this. There are some dark bits and some light bits, and that's probably about all you can tell. In 1609, Galileo Galilei made a telescope, and he was the first one, as far as we know, to point it to the heavens. And the first thing he looked at, as far as we know, is the moon. And he could see there were craters, and there's sort of a dark half and a light half. And this was pretty amazing and shocking to people. You might have heard, by the way, just as an off note, you might have heard of Galileo Galilei. Later measurements with his telescopes provided evidence that the Earth revolves around the sun. So we have the sun and the Earth revolves around it, and he was one of the first people to actually prove that. But he also made really nice maps of the moon. Fast forward 400 years, the Hubble Space Telescope also took nice pictures of the moon. So this is Galileo's picture. This is sort of a picture with a general nice telescope. And if you zoom in on this little crater region at the bottom, this is what Hubble saw. So this is that big crater, the Tycho crater. This happened when something big impacted the surface of the moon, and it spewed out all this dirt, basically, and then there were later little impacts around it. And the resolution, obviously, between Galileo to the Hubble Space Telescope is pretty crazy. So that's what 400 years and being able to go to space will do for you, although we don't only look at the moon, obviously. Seriously, telescopes, they just keep getting bigger. That's basically the trend. So this is a little chart that I made of some important telescopes and how big they were as a function of time. So time is down here on the x-axis, and the telescope size in inches is on the y-axis. Since I'm in Canada now, I know I can't get away with that, so I'll tell you. Hubble's Space Telescope was constructed around 1900. It was 100 inches, which is about 2.4 meters wide. With this telescope, he discovered some really interesting things. So Hubble discovered that the Milky Way galaxy is not the only galaxy out there, and that there were other galaxies. He also discovered 6 years later that the universe is expanding, which was extremely revolutionary. Fast forward a few decades, you have, so today some of the best, more than a few decades, today the best telescopes out there are basically the Keck twin telescopes. They're 10 meters, and there are 2 of them. So those were constructed around 1990, and they've contributed to some of the most groundbreaking science that we do. Hubble Space Telescope is smaller, so you can see this. So the general trend, right, of all of the telescopes is to go up, to get bigger with time. Hubble, because it's in space, you can't put a 10-meter dish in space. That's really hard. So it was small, and they compensated with a lot of other optics. But again, I mean, these 2 telescopes have really done a huge amount of work as far as astronomy in the past couple of decades is concerned. There was another one, the Kepler Space Telescope, was launched about in the last decade. It's found confirmed 1,000 planets and has 4,000 more in the can to analyze and figure out whether or not they're actually planets. And again, it's in space, so it's a little bit smaller. But there is this general trend towards larger telescopes, particularly on the ground. And that goes all the way to about 2022. And there's a big star up here. And one question you could ask is, what exactly is that telescope? It's up here at basically 30 meters. So this is a future telescope. There are a couple of really awesome telescopes that are going to be put together in the next couple of decades. So one of them is that 30-meter telescope. They're planning to put it in Hawaii. To give you an idea of how big 30 meters is, this is a tennis court. So it's about the size of a tennis court. It's actually a little larger than a telescope. There's also going to be a launch of the James Webb Space Telescope, which is one of these really cool, large, multi-segmented mirrors. This is the only way you can get a big telescope in space, basically, is to segment it. And that the expected launch date is sometime in the next 5-ish years. So we'll see about that. So these 2 telescopes together are going to answer some of the most fascinating questions we have in visible astronomy. What were the first bright objects that the universe produced? How did galaxies evolve? How did planets form? And of the planets we know, can any of them harbor life? And these telescopes are designed to answer questions just like that. So telescopes just keep getting bigger. So we started out with this measly little, 2-meter telescope about 100 years ago that discovered the universe was expanding, and going all the way up today to a 30-meter telescope that's looking at some of the faintest objects in the world. So telescopes, they really just keep getting bigger. But this is true for all wavelengths. So all of those different wavelengths, from super high energy gamma rays all the way to radio telescopes, they're all getting bigger. That's basically the trend. So in gamma rays, it turns out detecting gamma rays is difficult. So gamma rays form particle showers in the atmosphere. What this means is a gamma ray, one of these super high energetic particles of light, hits the atmosphere and makes a shower of basically a bunch of other light. So you have two ways of detecting that sort of light. One is to just measure them in space. So don't worry at all about these particle showers, and just put a big particle detector in space and get it before it ever hits the atmosphere. So that's one option. The other option is to actually blanket whatever region you're interested in, blanket it with detectors and actually measure this particle shower. And that allows you to go back and figure out where that gamma ray came from. So you can go back and say that came from an exploded star that's over there, that gamma ray came from some other exploded star that's somewhere else. So these are basically our two options. The two state-of-the-art experiments basically have, one is a space telescope, the other one deploys this sort of ground-based option. So the space telescope is called Fermi. That was actually the data from that made the gamma ray map. Yeah.
Why is it tragic?
Why is it tragic? Mostly if you, it's hard to make these detectors on the ground. It would be nice if you could just make one telescope and it detected a gamma ray instead of having to deal with all this whole particle shower stuff. It makes everything much harder. So this is the Fermi satellite. It detects gamma rays. There's sort of the state-of-the-art ground-based one is actually based in Namibia, and they have just a bunch of detectors on the ground. Fermi actually has an interesting near collision in 2012 with a defunct spy satellite. So when I was Googling things about the Fermi satellite, this picture came up and I got really scared. And then they're like, don't worry, no, it didn't collide, it's okay. So the operators of the Fermi telescope kind of managed to move it out of the way of this sort of space junk. But just so you know, space junk is a problem. We should probably worry about it more. So we have the Fermi space satellite. That's detecting gamma rays. Happily, it's still operating. That's great. We have this fun ground-based experiment that's state-of-the-art. So we're done, right? We don't have to do any more gamma ray astronomy. We're just finished. And that's not true. As is always the case, there's more stuff to measure. So there are a couple of interesting experiments that are on going to happen maybe in the near future. So one is definitely happening. This is the High Altitude Water Cherenkov Observatory. It's located in Mexico. It exists. So this is actually a picture of it. They basically have 300 tanks of water. These are huge tanks, right? They can fit a bunch of people in them, which obviously you shouldn't do when it's filled with water. The entire area of this is 200 meters by 100 meters. And each of these tanks holds 200,000 liters of water. I had to look it up. That's about 5 swimming pools per tank. It's a lot of water out in the desert. So this is basically online, and I think they're expecting to start taking data in the very near future. There's a somewhat more speculative one that's looking for funding in the. It's planned to be built in the Namibian desert. It's kind of an upgrade of a telescope that's already there. It's called the Telescope Cherenkov Array. So you may hear things about the CTA sometime in the next 5 years. Hopefully that thing is not that it didn't get funded, so you should forget about it, but we'll see. So in this case, the reason you go and you build these detectors is that bigger ones basically make better experiments. And in this case, that's more sensitive. So they are more sensitive. They can figure out what energy the particles are much more accurately, and they can figure out where they came from much better. So that basically just allows you to make a better telescope out of these ground-based detectors. That turns into better images of all these high energy objects, these collisions and stars exploding and stuff. stuff. And that turns into more clues about these sort of intense particle accelerators that exist in the sky. Okay, so great. So that's the future of gamma ray astronomy.
What does water do?
Sorry?
What does the water do?
It's true, I skipped over that part. So what they do, so good thing you caught me on that. So when the particle goes through the atmosphere, this stuff that comes off, that's actually light. And it's light that's a special kind of light that's called Cherenkov light. And it happens at a particular angle off of the shower. So what you do is set up a bunch of water basins, and the light hits the water at this particular angle, and you detect it with just light detectors. So they're called photomultiplier tubes, but they basically just detect light. So the water allows you to detect this light better, and then the actual thing that detects it are just little photomultiplier tubes. But you can Google it, Cherenkov detectors. They're really cool. Oops. All right. But there's a lot more astronomy where that came from. So there's X-ray astronomy. It turns out X-rays are just stopped in the atmosphere, full stop. So we can't do this fun thing with Cherenkov light or anything. We just have to go directly to space. So the Einstein satellite was launched in 1979. It made some pretty great measurements of different X-ray sources. For example, the Crab Nebula is one of them, and you can see the Einstein image here on the left. In 1999, the US launched the CHANDRA X-ray Observatory. This made much higher resolution, much finer measurements of these X-ray sources. So this is the equivalent Chandra image of the same Crab Nebula. And you can just see it's a much higher resolution image. So this is quite an improvement in those 20 years. So obviously, since I worked on Chandra for a little while on some Chandra data, I decided to take a small break and look at some nice Chandra images. So this is the Crab Nebula. It turns out most X-ray sources or a lot of X-ray sources are just stars that exploded at some point. So in 1024, Chinese astronomers saw a star explode, and this is its remains. We call it the Crab Nebula. In 1181, a star exploded, and Chinese and Japanese astronomers saw that, and this is its remains. And in 1572, Tycho Brahe saw a star explode, and this is the remains. So X-ray astronomy, so these are false color, obviously, but X-ray astronomy can really zoom in and get these really fine measurements of these X-ray sources.
So these are supernovas?
These are, yeah, the remains of a supernova, yeah.
How long does a supernova is supposed to take time? I mean, does it mean that if the Chinese see it, it was not there when the Europeans...
Oh, I see. I don't know how far away each of these individual things is. So they're many light years away, right? So in time, they exploded a long time ago. We saw their light, whatever that was, 1,000 years ago or so. These are just kind of its remains. So I think supernova in general explode within a couple of days, up to a week, and then you're just kind of left with the remains. Okay. But X-ray astronomy is not done. There are still instruments that are being built and things that are being flown. So NuSTAR was launched in 2012. It has this really interesting design. All of its detectors are on this side, and its mirrors are over here, and there's this long kind of boom arm between them. And that allows for better focusing power. And there's a eROSITA satellite that they're planning to launch in a couple of years, which is basically a lot of Chandras. So this gives you much better sensitivity, much better resolution. So you can just really see these X-ray sources much, much better. So that gives us, again, better images of all these high to medium low energy objects. And that gives us more clues about these black holes, these things that are so dense that not even light can escape, and other super high energy phenomena. So X-ray astronomy, also some fun things coming up in the horizon. So telescopes have been getting bigger at all wavelengths. It turns out that to detect a given bit of light, that depends on how big its wavelength is, right? So for an optical bit of light that's hitting my telescope, I could have a telescope that's whatever size, let's call it this. If I'm trying to detect light with a wavelength that's the size of a building, I need a much bigger telescope to see that, just much larger area of my telescope to sort of capture that photon. So bigger wavelengths need even bigger telescopes. So radio astronomers knew this. In radio, the biggest single dish telescope is in Arecibo, that's in Puerto Rico. It's a 305 meter diameter dish. I looked it up. That's 5 hockey rinks across. In sort of the 60s, radio astronomers discovered that they didn't need one huge dish. They could actually take a bunch of little dishes and just spread them out. And if they do it in a clever enough way and take their data in a particularly clever way, that will equal one large dish. So they built a variety of these sort of interference telescopes. One of them is the Very Large Array. If anyone's seen Contact, that means you've actually seen a picture of it. It has a 36 kilometer diameter. So that means one dish is 36 kilometers away from the other dish. I looked it up. That's the distance between here to Mississauga. So that's like we put one telescope here, one telescope in Mississauga, and then maybe a few in between here and there. Astronomers figured out that you didn't need to be able to take all of these telescopes and put them together with a cable. You could just take data with one telescope and another telescope, and if you did it carefully enough, you could figure out what you were looking at later. That's called very long baseline interferometry. So that combines telescopes on entirely different sides of the world. So recently, one of the University of Toronto professors had a measurement that's one of these VLBI measurements between a telescope here near Toronto, Germany, and India. So that gives you some really interesting results, and you can do a lot of stuff with it, and that's great. But this is a pretty amazing feat of technology that you can take telescopes from across the world and then measure some little source off at infinity with them. Fun fact, the first VLBI ever was done in Canada. It was done between the Algonquin telescope, which you might have heard of if you've ever gone to the Algonquin Park in Ontario. It's like 7 hours north of here. And the Dominion Radio Astrophysical Observatory, which is in BC. So that was the first VLBI, one of these long baseline things ever done. That was about 1967. I happened to, for entirely different reasons, redo that measurement over the summer. So I'm just gonna say these are my own pictures of the telescope. So this is Algonquin Radio Observatory, and this is actually me putting a feed on it. And this is the DRAO, the Dominion Radio Astrophysical Observatory, and this is me putting a feed on it. So I accidentally redid this without knowing what I was doing. But the first VLBI ever was done in Canada, and this was a huge achievement in radio astronomy. So we're still not done with radio astronomy. Those telescopes are getting bigger too. So one really cool experiment, and I'll say that because I work on it, is CHIME. So it's a 100 meter by 100 meter telescope that we're putting up in Penticton in British Columbia. And this is exploring this mysterious dark energy that's causing the universe to expand and that expansion to accelerate. There's also a huge radio array that's coming together. It's called the Square Kilometer Array, SKA. It is not in fact a square kilometer. It's 5 kilometers by 5 kilometers. And they're building one in Africa and one in Australia. And this has a huge number of science goals just because it's both an enormous array and it covers a huge set of radio wavelengths. Some of the science goals are what were the first bright objects in the universe and can planets harbor life? So this will also be able to help answer those questions. So scientists are using these enormous telescopes to answer some of the most fundamental science questions that we have. These are including but not limited to what's happening with this expansion in our universe? Can other planets harbor life? What was the universe like when it first started? What made the first stars? And was Einstein right about gravity? So these are some of the questions that are facing current scientists, and we're hoping to answer them with this new set of enormous telescopes that we're building at all these different wavelengths. But I started with a slightly more mundane question than all of those really big ones. So I started out with what is going on with Centaurus A. So I said it's a galaxy, it's currently consuming a nearby galaxy, and it contains a supermassive black hole in its center. And I asked the question, how do we know all of that? And the answer is we look at it with telescopes at all these different wavelengths. So Centaurus A in the visible looks like this. It's mostly stars, it has this sort of bright center, and then it has a bunch of dust in the middle, and that dust means that we can't really see the starlight on the other side. It's obscuring the light from getting to us. So we kind of see like a big light blob with this little streak in the middle. I'm not an optical astronomer, so maybe they see other things too, but that's what I see. If we look at it instead with a gamma ray telescope, so one of these ridiculously high energy, so we're looking at this high energy light, we see this sort of diffuse purple stuff. So this, well, it's purple in this picture. So it's a purple haze. This is gamma ray emission coming from Centaurus A. This is one of the ways we know that it has a supermassive black hole in its center. One of the ways you get this enormous emission, this is light years across, is to have a black hole that's like accreting matter on it. So the black hole's kind of swirling matter around it and then shooting that up at high energies. And that gives you these sort of lobes from the sort of shooting up of all this light. If we look at Centaurus A in X-ray, so at slightly longer wavelengths, we see the center and then this jet. And this is actually the jet of matter. It's the same thing as just what's in this artist depiction, shooting out of Centaurus A. So this is another clue that there's something, some supermassive black hole or massive black hole at the center of this galaxy. If we go all the way down to radio emission, we see the center, so this is very long wavelength. We see the center of the galaxy. We get these lobes, and that's just because they emit at basically all wavelengths. And then there are some additional things coming from sort of that dusty disk in the center that was obscuring all of that light. So when we put all of this together, we figure out that there's a supermassive black hole at the middle of Centaurus A, and it's shooting a bunch of stuff out of it, and that is what we learn from all these different things. So that's the answer to the question. Just to put it all together in an even prettier picture, the visible starlight, or sort of this white, sort of these white stars. The gamma rays are this big red diffuse emission. The X-rays have this jet of light coming out of the center, and then radio has these sort of green lobes, and then this disk in the middle. Okay. So I started out by saying light is a wave. We use light to understand things about our universe and about Centaurus A, and maybe about planets, and maybe about life, and maybe about the future of the universe. There are other things that are waves, right? Water is a wave, slinkies have waves. It turns out gravity can also have waves, and this is a really interesting direction for an astronomy detector. So there's this experiment called LIGO, the Laser Interferometer Gravitational Wave Observatory. We all just call it LIGO, so I don't have to say all that. It's a couple of stations that use lasers to detect gravity waves. So they have a single station, and then they have a bunch of tubes that go out at right angles, and they shoot laser light down these tubes. The reason they do this, because it's a good question why they would do this, is if you have out in space some kind of black hole swirling around another black hole or something like that, that interaction between those two extremely massive heavy things makes gravity waves. I won't tell you how, you'll just have to believe me. So it makes gravity waves. Those gravity waves propagate through space, and they propagate through the Earth. And if you run extremely finely tuned lasers along these lines, you can see a difference. If the gravity wave sort of goes through these laser lights and torques one of them with respect to the other, you can use that to detect gravity waves. Mostly so far they've detected like trucks driving down the road over them. But the next generation of LIGO, that will not be true. They all promise us that. So this is sort of one of the interesting directions of astronomy, is to go from using light to detect stuff in the universe to using gravity itself to detect stuff in the universe. So light is a wave and gravity is a wave, and hopefully we'll get to just use all of these waves to understand things in our universe. So with that, I will end. and I'm supposed to show this.
We have a couple minutes for more questions for Laura.
Yeah, sure.
One thing for the ground-based telescopes, instead of building new arrays, why is it we don't put way more cost steps to improve the technology to existing arrays? Like for the very large array,
Oh.
why don't we make it bigger as opposed to making it a separate one entirely?
So it sort of depends. For the VLA, they do. So they upgrade their receivers. Oh yeah, sure. So he basically asked, why would you make more telescopes when you can just improve the stuff that's on the current telescopes? And the answer is sort of twofold. So for something like the VLA, where they put a lot of money into it, and the telescopes are good, I mean, there's no reason to replace them. They do replace the equipment, right? So all the detectors and stuff that make an instrument sensitive, they replace those. I think they just finished upgrading it not that long ago. So they replace all of that stuff, especially in radio astronomy, where the most expensive part of it all is sort of the computer side of it. So it's what you use afterwards, after you actually like take your signal and put it into a computer. And that of course changes, I mean, the time scale for computation getting faster is very small. So they change that quite a lot. So the other reason is, so for these optical telescopes, you can't really build, the dish is really expensive, so if you're going to get a bigger dish, you might as well just build another telescope, because you probably need to make better motors and stuff. So it's kind of whether or not you decide to just upgrade what you currently have or make a whole new thing, it's sort of a question of what wavelengths are you talking about, what actually is the cheapest and best option, and also what are your science goals. So like CHIME, which was the last thing that okay, now it's a while ago, I'm sorry that I'm doing this. So CHIME is a totally new thing. We need to build it all from scratch because no one's built anything like it before. So it's kind of it's a good question, like what do you do? And it's usually whatever is cheapest is the thing you do. Yeah. Yeah.
Is it known how big Centaurus A is, like in light years?
Oh, I am sure it's known. I don't know it. So the Milky Way also has radio lobes. So we also have those things that are shooting out of the center. That's actually what that galactic spur that you guys may not remember, I went on and on about it. That's like 100 million light years wide, long, I mean.
1,000, right?
Maybe. I would Wikipedia it. So I don't know the size of Centaurus.
Which is a giant elliptical.
Okay. I should just say I'm a cosmologist, so the things that I know about actual objects in the sky is pretty minimal. Yeah, sorry. Oh, yeah, you.
Can gravity waves be detected from space?
From space, yeah. So that was the next thing that they. So they don't have funding for it now, but there was a plan to take LIGO. So it's this guy, and they were going to do that, but in space, because you can put them further away. You don't have to worry about trucks. There are a lot of good things. So it's much more expensive to do it. So it is a good idea, but they're sort of looking for funding. I think you had a question.
With BICEP 2 recently discovering the
Sure.
polarization of light, and then big news for everybody.
Yeah.
What exactly is the technology behind that telescope, and how does it compare to other telescopes that are trying to detect gravitational waves?
Yeah. So BICEP is a microwave telescope that's located in the South Pole. It had this year a pretty important result that we're sort of waiting for confirmation to see if it's true. If it's true, it's a signature of gravity waves that were made in the very beginning of the universe, in the first second that the universe existed. It made these gravity waves, and BICEP might have detected a signature of that. LIGO would be able to be, not LIGO, a larger version of LIGO or a space-based one would eventually be able to detect that background of gravity waves. And it's an interesting way of doing it, but not for years. So a microwave-based detector is definitely the way that you'd go for the next sort of 20 to 30 years, probably. The technology that you use is very different. So the detectors are cryogenic. It's all microwave-based stuff. BICEP was you needed like a 1 meter telescope, basically. I think even smaller than that. So there are a bunch. I actually have it. There are a bunch of telescopes that are sort of going after this signature. These are sort of the newest ones. So we put them either in the Atacama Desert, you fly them on a balloon or put them in space, or you stick them in the South Pole. They all use roughly equivalent detector technologies at this point. We've all kind of converged as a field. So this is what I did as a postdoc, and I'm currently on this experiment. Did I answer your question?
Yes.
Okay. Yeah.
How long is a gravity wave?
Sorry.
How long is a gravity wave?
How long is a gravity wave? Yeah, so they measure it in like hertz, and it's like 10 to the -7 or something hertz. So they're very long frequency. It's a very long frequency, very long wavelength. That's what I mean.
One more question.
Yeah.
What types of observations can you make with these telescopes to include that planets can support life?
Yeah, that's an excellent question that I probably shouldn't answer. So mostly what they're looking for is some kind of what we call a spectroscopic signature. So you take a telescope that has detectors at multiple frequencies, and you use that to try to tell what the atmospheres of the planets are. So like if it's methane, is it oxygen, is it something like that?
Like mass spectrometry.
Yeah, exactly. And there are probably a million clever ways that all of these things are planning to do it. And some of their claims may be exaggerated, but for the optical telescopes, I'd believe it. For the radio ones, we'll see. But yeah, that's right.
Let's thank Laura again.
Sorry.